Hi, we're gonna discuss some of the results that we got for the linear static simulation that we did for the trolley, for this trolley here. So we simplify the model to just represent what is important. So basically will be, we analyze the deformation and the stresses that we have, particularly in this area. That's where the wheel actually rests. So the first analysis we have here is the stress bond misses, which is the base of comparison that I use to actually check whether the design will withstand the load of the wheel. So we see a total bond misses of 12.68 megapascals, which if we compare that number to the yield point of aluminium, which is between 300 and 400 megapascals, we see that we are in safe in terms of elastic deformation. So we are in the low side, not even close to the yield point, or where we start with the to see plastic deformation. Here in this second scenario, which is also the bond misses, we see details of where the higher concentration of stresses are. So we got, of course, here on these two sides, we don't have any support in between these two members. So, and that's where the actual tire will rest. So that's somehow expected. We also got some high stresses on these corners around here. So that's somehow the behavior that I will be expecting from this model. So these arcs here also show like higher concentration of stress. In terms of how I built the model, I basically constrain all these edges. They are fully constrained because in real life they will be welded to the square hollow sections. So I didn't left any degree of freedom on these corners, and also here at the bottom of these members. And of course we have a load in this direction, so I call it the minus Z direction of 1700 newtons, which is we are assuming a weight for the wheel of 180 kilograms. Here we have another scenario, which is the stress, but this is the maximum principle, so a little bit different to the bond misses. This actually shows us where the higher concentrations of stress are. So these two areas, they although they have higher concentration of stress, it is not as high as what we have in these corners and in the arcs here. So that's what we have here, which is the maximum stress principle, which is still within the same range of what the bond misses analysis is. Now the other analysis we have here is displacement. So if we look at here, it's somehow what we will expect, since there is no supports of anything that stopped this aluminum sheet from deforming when we place the tire. We have a quite pronounced displacement here. However, this is actually the effect of the deformation is actually scaled to a higher number, to a higher percentage. The maximum displacement is only 0.368 millimeters, which is also not very high. So yeah, the color code just shows that there's very low displacement on this area, between 0.03, this blue area, and then we got the green part with 0.20 and then 0.36 for this area, since we have a quite big span here without supports. Now, some assumptions for this simulation, there is things that can be improved, but yeah, they probably need more time for sort of refine the model and get more accurate results. Well, the first assumption that we got was the material. This is an aluminum 2014, but of course, depending on the alloy of the aluminum, the results can slightly change because of different physical properties, density, the Young modulus, etc. So for this particular case, I used 2014 aluminum. For this simulation, we actually took here the load or the weight of the wheel to be distributed in all these aluminum sheets, but we can actually simulate another scenario where we have like regional load when all the weight will be concentrated only within this area. So after this, like within this span, so there will be more like concentrate load, like regional load, instead of a whole surface load. What else? We consider that the wheel was actually put it from the trolley. It was actually put it on the stand, but I haven't tested like when the wheel is dropped from a certain height. To do that scenario, I might double up the weight of the wheel just as an approach for that scenario if required. This model was simulated as a single part, so if you see here is sort of merge areas, but in the real life this sheet is welded to the frame, so it might slightly change the results. So I will take the stand as one part and then assemble the sheet on top and use something like new constraint for like contact surfaces as a connection between these two parts. The software that I use to do this simulation is Cryoparametric, which limitates the things, the sort of constraints that I can put to the model, because I am only running it in the light version, which limits the number of surfaces that I can model and doesn't allow me to control the size of the mesh or select between a single pass or multi-pass analysis. So for the second test, I will try to run it in ANSYS Workbench or even SolidWorks simulation module. It will be also interesting to add some constraints here on this corner, like rotation constraints, to see what is the concentration of loads in this connection here. So I haven't considered that in this simulation. That'll be interesting to see what happened when I include it. So basically, in summary, we got the model here. We put some constraints on the frame, full constraints on the sides, load of 180 kilograms, and we are getting results in the very low side, 12, like almost 13 megapascals versus 300, 400 megapascals of yield point. So we're very safe. And then, yeah, we were expecting for elastic deformation, and that's what we're getting. Thank you.